January 22nd, 2026. Hubble captured the interstellar object 3I Atlas during an almost perfect Sun-Earth and the object alignment. That geometry should have erased any sunward-pointing feature, yet the jet remained offset, defying expectations based on dust dynamics and projection. If this was the ultimate test, why does the data not match the theory? The answer begins with a single, stubborn anomaly. Opposition brings a rare alignment. The Sun, Earth, and the interstellar object, 3I Atlas, form a nearly straight line in space. On January 22, 2026, the phase angle between Earth and the interstellar object dropped to just 0.69 degrees. Under these conditions, any structure pointing directly toward the Sun should appear dramatically foreshortened, almost vanishing from our view. Features that normally stretch outward become compressed along the line of sight, their length and brightness altered by this extreme geometry. This is more than a visual trick. It is a physical test. If a dust jet really shoots sunward, perfect alignment should flatten it into a narrow spike, or even erase it completely from the image. Instead, opposition acts like a filter, exposing which structures are truly radial and which are shaped by other forces. The expectation is clear. Pure sunward features should collapse under this geometry. Earlier images of 3I Atlas challenged expectations from the start. Most dust structures in active interstellar objects, when viewed from Earth, stretch away from the Sun, driven by solar radiation pressure rather than toward it. Yet in the weeks before opposition, observers noticed a persistent feature that seemed to extend sunward, cutting against the usual pattern. This raised an immediate question. Was this a genuine outflow of material or a trick of geometry? In some cases, dust released along the object's orbit can project as a sunward spike when viewed from the right angle, creating an anti-tail illusion. But the possibility of a real asymmetric jet could not be ruled out, especially given reports of wobbling activity and a measured rotation period of 15.5 hours. The ambiguity in these early frames set the stage for a deeper investigation, requiring higher resolution data to distinguish illusion from physical process. Hubble's view stands apart for its ability to resolve fine structure in faint, distant objects. With a resolution of just 0.05 arcseconds, it can distinguish features as small as a few hundred kilometers across at the distance of 3I Atlas. This clarity is essential when the goal is to separate real dust structures from background noise or processing artifacts. In the crowded star fields near opposition, Hubble's stable, space-based optics avoid the blurring and distortion common to ground-based telescopes. The result is a level of detail that allows astronomers to track subtle changes in jet orientation and brightness, critical for testing whether a feature is truly sunward or shaped by more complex dynamics. To confirm the reality of the feature, astronomers turned to Larsen-Sechenina filtering, a method designed to highlight subtle structures by comparing the brightness at each angle around the nucleus. This approach strips away the smooth coma and brings out any true jets or asymmetries. In the filtered images, the offset structure stands out clearly, not just as a faint suggestion, but as a persistent ridge. Its length measures close to 100,000 kilometers, far beyond what random noise or background stars could produce. The fact that the feature survives this kind of enhancement, retaining its shape and orientation, signals that it is a genuine part of the object's dust environment. The processed image from January 22, 2026, credited to Toni Scarmato, brings the puzzle into sharp focus. Even under near-perfect alignment, the offset ridge stands out, tilted, persistent, and refusing to collapse into the symmetry predicted by textbook geometry. The expectation was clear. A jet truly aimed at the Sun should shrink into a thin, almost invisible line or vanish entirely. Yet the structure holds its angle, echoing the orientation seen in earlier images. Geometry alone cannot account for this stubborn offset. The image itself becomes evidence, raising questions about what forces are shaping the dust and defying the simplest models. In the right panel of the processed January 22 image, 3 distinct spokes can be traced, each marked by a position angle. One is at roughly 0 degrees, the others are near 120 degrees and 240 degrees. These angles are not random. They appear nearly evenly spaced, suggesting an underlying pattern. Instead of a single jet, the evidence points toward multiple features radiating from the nucleus. This arrangement could reflect rotating outflows, dust shells shaped by spin, or a complex interplay of dust and viewing geometry. The presence of 3 stable position angles deepens the puzzle, and it hints that the visible structure is more than a simple sunward jet. Several grounded explanations remain in play. Projection geometry, a classic anti-tail illusion, where dust along the orbital plane appears sunward because of the viewing angle near opposition. Anti-velocity dust, with slow-moving grains lingering in the object's wake and creating offset features. Rotating asymmetric jets, shaped by the nucleus spin and by localized active regions, which could produce multiple, apparently stable directions. Image enhancement effects, for example Larsen-Saccanina filtering, which can exaggerate gradients and make subtle structures stand out more than it truly is. Each hypothesis draws on known dust physics or on processing effects, and each carries its own uncertainties. Even in perfect alignment, 3I Atlas defies our dust models. The data remains unresolved. As new interstellar visitors arrive, our theories face a challenge that has only just begun.